purpose of having two circuit breakers in series for a control panel in NFPA 20 is not to provide redundancy, but to fulfill different functions. An isolation circuit breaker is typically rated at a higher amperage and serves as the main disconnect for the control panel. It is used to isolate the panel from the incoming power source in case of maintenance or emergencies. A short circuit circuit breaker is rated at a lower amperage and is located downstream of the isolation circuit breaker. Its purpose is to protect the control panel and its components from short circuits that may occur within the panel. Let's look at why two circuit breakers are needed. Firstly, isolation. The isolation circuit breaker allows for safe maintenance or replacement of the control panel without having to disconnect the incoming power. Secondly, protection. The short circuit breaker trips quickly in the event of a short circuit, limiting the current flow and preventing damage to the panel and its components. Thirdly, overcurrent protection. The isolation circuit breaker provides basic overcurrent protection, but the short circuit breaker offers more sensitive and faster protection against high current faults. Now let's talk about why you can't use one circuit breaker with both functions. Using a single circuit breaker with both isolation and short circuit protection functions is not recommended for the following reasons. Firstly, reduce safety. A single circuit breaker may not be able to perform both functions effectively, potentially compromising safety. Secondly, increase cost. A single circuit breaker with both functions would need to be rated for the highest current of both the isolation and short circuit circuits, leading to a more expensive and bulky unit. Thirdly, compromised reliability. If the single circuit breaker trips for any reason, both isolation and short circuit protection would be lost, leaving the panel vulnerable. In summary, having two circuit breakers in series for control panel in NFPA 20 provides both isolation and short circuit protection, ensuring safety, reliability, and flexibility during maintenance and emergencies. Circuit breakers are essential components in electrical systems, designed to protect circuits from damage caused by overcurrent or short circuits. They are electromechanical devices that automatically interrupt the flow of current when a fault is detected. Understanding their operation types and applications is crucial for electrical safety and system reliability. A circuit breaker operates on the principles of electromagnetism and thermal expansion. When the current in a circuit exceeds the breaker's rated current, a mechanism is triggered to open the circuit. There are two primary mechanisms for tripping a circuit breaker: thermal and magnetic. Thermal circuit breakers use a bimetallic strip that bends when heated by the current flowing through it. If the current is excessively high, the strip bends sufficiently to release a latch, which causes the breaker to trip and interrupt the circuit. These breakers are designed to protect against sustained overloads. Magnetic circuit breakers use an electromagnet to trip the breaker. When a short circuit occurs, the sudden surge of current creates a strong magnetic field that pulls a lever, causing the breaker to trip. Magnetic breakers respond very quickly to high current faults, providing rapid protection against short circuits. There are several types of circuit breakers, each designed for specific applications and current levels. Miniature circuit breakers, or MCB, are commonly used in residential and commercial buildings for branch circuit protection. They are designed to protect individual circuits from overcurrent and short circuits. MCB are typically rated for currents up to 100 amps and voltages up to 480 volts. Molded case circuit breakers, or MCCBs, are used in industrial and commercial applications for protecting feeder circuits and equipment. They have higher current and voltage ratings compared to MCB, typically up to 2500 amps and 600 volts. MCCBs offer adjustable trip settings, allowing them to be customized for specific applications. Air circuit breakers, or ACB, are used in high current applications, such as main switchboards and power distribution systems. They use air as the insulating medium and are capable of interrupting very high fault currents. ACB are typically rated for currents up to 6,300 amps and voltages up to 1,000 volts. Vacuum circuit breakers, or VCB, are used in medium voltage applications such as substations and industrial plants. They use a vacuum as the insulating medium, which provides excellent arc quenching properties. DCB are typically rated for voltages from 1 kV to 38 kV and currents up to 4000 amps. Residual current devices, or RCD, also known as ground fault circuit interrupters or GFCIs, are designed to protect against electrical shock. They monitor the current balance between the supply and return conductors and trip if there is a difference, indicating a leakage current to ground. RCD are commonly used in bathrooms, kitchens, and outdoor areas where there is a risk of electric shock. Circuit breakers are essential for electrical safety and equipment protection. They are used in a wide range of applications, including residential, commercial, and industrial settings. In residential buildings, circuit breakers protect branch circuits from overcurrent and short circuits. They are installed in electrical panels and provide a convenient way to reset a trip circuit. In commercial buildings, circuit breakers protect lighting, power, and HVAC systems. They are used in distribution boards and control panels to ensure the safe and reliable operation of electrical equipment. In industrial plants, circuit breakers protect motors, generators, and transformers. They are used in motor control centers and switchgear to prevent damage from overloads and short circuits. Selecting the correct circuit breaker for a specific application is crucial for ensuring safety and reliability. The following factors should be considered when selecting a circuit breaker current rating. The circuit breaker's current rating should be equal to or greater than the maximum current that the circuit is expected to carry. Voltage rating. The circuit breaker's voltage rating should be equal to or greater than the voltage of the circuit. Interrupting capacity. The circuit breaker's interrupting capacity should be greater than the maximum fault current that the circuit could experience. Trip curve. The circuit breaker's trip curve should be appropriate for the application. Thermal trip curves are suitable for protecting against sustained overloads, while magnetic trip curves are suitable for protecting against short circuits. Environmental conditions. The circuit breaker should be suitable for the environmental conditions in which it will be installed, such as temperature, humidity, and altitude. Circuit breakers are vital for maintaining electrical safety and protecting equipment from damage. Regular inspection and testing are essential to ensure that circuit breakers are functioning correctly. The following maintenance tasks should be performed regularly. Visual inspection. Inspect the circuit breaker for any signs of damage such as cracks, corrosion, or loose connections. Operational testing. Trip the circuit breaker manually to ensure that it operates correctly. Insulation resistance testing. Measure the insulation resistance of the circuit breaker to ensure that it is within acceptable limits. Contact resistance testing. Measure the contact resistance of the circuit breaker to ensure that it is low enough to prevent overheating. Trip time testing. Measure the time it takes for the circuit breaker to trip under different fault conditions. NFPA 70E, the standard for electrical safety in the workplace, provides guidelines for safe work practices when working with electrical equipment, including circuit breakers. The standard emphasizes the importance of energizing equipment before working on it and using appropriate personal protective equipment or PPE. Arc flash studies are often conducted to determine the potential hazards associated with working on electrical equipment and to select the appropriate PPE. Circuit breakers play a critical role in arc flash protection by quickly interrupting the flow of current during a fault, reducing the duration and severity of an arc flash event. Advances in circuit breaker technology have led to the development of smart circuit breakers that offer enhanced monitoring and control capabilities. Smart circuit breakers can communicate with a central monitoring system, providing real-time data on current, voltage, and temperature. They can also be remotely controlled, allowing for remote tripping and resetting. Smart circuit breakers can be used to improve energy efficiency, reduce downtime, and enhance safety. In conclusion, circuit breakers are essential components in electrical systems, providing protection against overcurrent and short circuits. Understanding their operation, types, and applications is crucial for electrical safety and system reliability. Regular inspection and testing are necessary to ensure that circuit breakers are functioning correctly. As technology advances, smart circuit breakers are offering new opportunities for improving electrical system performance and safety. Selecting the right circuit breaker involves several key considerations to ensure optimal protection and reliability for the electrical system. Firstly, determine the continuous current requirements of the circuit. This involves calculating the total load that the circuit will carry under normal operating conditions. The circuit breaker's ampere rating should be at least 125% of the continuous load to account for potential overloads and prevent nuisance tripping. For example, if a circuit has a continuous load of 16 amps, the circuit breaker should be rated for at least 20 amps. 16 amps times 1.25 equals 20 amps. Secondly, evaluate the voltage requirements of the circuit. The circuit breaker's voltage rating must be equal to or greater than the voltage of the circuit. Using a circuit breaker with a low voltage rating can result in failure and potential safety hazards. For example, a 240-volt circuit requires a circuit breaker with a voltage rating of at least 240 volts. Thirdly, assess the available fault current at the installation location. The circuit breaker's interrupting rating, also known as its short circuit current rating, must be greater than the maximum fault current that could occur at the installation location. This rating indicates the maximum current that the circuit breaker can safely interrupt without failing. Using a circuit breaker with an insufficient interrupting rating can lead to catastrophic failure during a fault, potentially causing significant damage and injury. Fault current studies are often conducted to determine the available fault current at various points in an electrical system. Fourthly, consider the trip characteristics of the circuit breaker. Circuit breakers are designed with different trip curves to provide appropriate protection for various types of loads. Inverse time circuit breakers provide overcurrent protection and trip time decreases as the current increases, providing protection against overloads and short circuits. Instantaneous trip circuit breakers trip almost immediately when a fault occurs and provide rapid protection against short circuits. Time delay circuit breakers allow for short duration overloads without tripping and are suitable for circuits with inrush currents such as motor circuits. Fifthly, select the appropriate type of circuit breaker for the application. Miniature circuit breakers (MCB) are commonly used for branch circuit protection in residential and commercial buildings. Molded case circuit breakers (MCCBs) are used for feeder circuit protection in industrial and commercial buildings. Insulated case circuit breakers are used for main circuit protection in large industrial and commercial installations. Air circuit breakers (ACB) are used for high current applications in power distribution systems. Vacuum circuit breakers (VCB) are used for medium voltage applications in substations and industrial plants. Sixthly, consider any applicable codes and standards. Electrical installations must comply with relevant codes and standards, such as the National Electrical Code (NEC) in the United States and the Canadian Electrical Code (CEC) in Canada. These codes specify requirements for circuit breaker selection, installation, and protection. Seventhly, evaluate the environmental conditions at the installation location. Circuit breakers must be suitable for the environmental conditions in which they will be installed, such as temperature, humidity, and altitude. Dating factors may need to be applied to the circuit breaker's current rating if it is installed in high-temperature environments. Eighthly, consider the need for additional features and accessories. Some circuit breakers are available with additional features, such as shunt trips, undervoltage releases, and auxiliary contact. Shunt trips allow the circuit breaker to be tripped remotely. Undervoltage releases cause the circuit breaker to trip when the voltage drops below a certain level. Auxiliary contacts provide remote indication of the circuit breaker's status. Accessories such as terminal lugs, mounting hardware, and enclosures may also be required for the installation. Finally, consult with a qualified electrical engineer or contractor. Selecting the right circuit breaker can be complex, and it is important to seek expert advice to ensure that the selected circuit breaker is appropriate for the application and complies with all applicable codes and standards. Understanding the difference between an isolation circuit breaker and a short circuit breaker involves looking at their specific roles and characteristics. An isolation circuit breaker, often referred to as a main disconnect, is primarily used to isolate the electrical panel or equipment from the main power source. It is designed to provide a safe means of disconnecting power for maintenance, repairs, or emergencies. Key features include a higher amperage rating compared to branch circuit breakers to handle the total load of the panel. It's typically manually operated, meaning it's switched on or off by hand. It serves as the main point of disconnection, allowing technicians to safely work on the downstream circuits without the risk of electrical shock. A short-circuit circuit breaker, on the other hand, is designed to protect the electrical panel and its components from damage caused by short circuits or overcurrent conditions. Key features include a lower amperage rating compared to the isolation circuit breaker, sized to protect the specific branch circuit it serves. It operates automatically, tripping quickly in response to a sudden surge of current caused by a short circuit or overload. It limits the amount of current that flows through the circuit during a fault, preventing overheating, fire, and damage to equipment. Functionally, the isolation circuit breaker is like a master switch for the entire electrical panel. It's used to disconnect power to the panel when needed for maintenance or safety reasons. The short-circuit circuit breaker is like a safety valve for individual circuits within the panel. It protects against faults by quickly interrupting the current flow. The location of these breakers within the electrical system is also important. The isolation circuit breaker is usually located at the main point of entry for the electrical supply, such as at the top of the electrical panel. The short-circuit circuit breakers are located downstream of the isolation circuit breaker, each protecting a specific branch circuit. The two breakers work together to provide a comprehensive protection scheme. The isolation circuit breaker allows for safe disconnection of power, while the short-circuit circuit breakers protect individual circuits from faults. In a typical scenario, if a short circuit occurs in a branch circuit, the short-circuit circuit breaker will trip, interrupting the flow of current to that circuit. This prevents damage to the wiring, equipment, and the rest of the electrical system. If maintenance is required on the electrical panel, the isolation circuit breaker can be switched off to de-energize the entire panel, providing a safe working environment for technicians. Consider an example in a residential setting. The main breaker in the electrical panel acts as the isolation circuit breaker, allowing the homeowner to shut off power to the entire house for electrical work. The individual circuit breakers protecting the lighting, appliance, and outlet circuits act as short-circuit circuit breakers, tripping in response to faults in those circuits. Similarly, in an industrial setting, a main disconnect switch acts as the isolation circuit breaker for a piece of equipment, while individual circuit breakers protect the motor control circuits and other components. The isolation circuit breaker allows for safe maintenance and repair of the equipment, while the short-circuit circuit breakers protect against faults. The use of two circuit breakers in series provides both isolation and short-circuit protection, enhancing safety and reliability. The isolation circuit breaker allows for safe disconnection of power, while the short-circuit circuit breakers protect individual circuits from faults. This combination ensures that the electrical system is protected against a wide range of potential hazards.